So everyone can see the screen and hear me, right? अफान आवाज आ रही है? Zaina, Amna, can you hear me?
Yes.
अच्छा चलो so we're just doing isomers, right? We had people. So now we were doing isomers, and I told you that there was a cis-trans version of an isomer, right? Which was like this was cis and this was trans. We discussed all of that, right? So the arrangement in a complex line, it could have a cis or trans arrangement, and we did square planar as well. There was a specific, you have to remember this specific example of a square planar complex, right? So specifically cisplatin and transplatin. So you could have the two CLs on the same side, that was your cis version. You could have two CLs on opposite sides, that's your trans version. And I explained to you that cisplatin was used as an anti-cancer drug, that it would, so I'm just going to write it over here, that cisplatin um, combines with the DNA bases. And when it does that, it prevents further replication. Okay, so that prevents further replication. That was his plot. Now, so that is geometric isomerism. Then there's another thing which is called optical isomerism. That's the whole chirality thing, the mirror images. So you've got optical isomers. That's the second part. So you've got optical isomers in complex molecules as well. So optical isomers is, remember, um, they're basically non-superimposable mirrored versions, right? Like your two hands are optical isomers of each other. They're non-superimposable. The they're mirrored versions of each other. So in organic chemistry, you had chirality, right? You have something similar over here as well. So if you have a complex, and optical isomers normally happens with bidentate ligands. So if I have a, let's say I have an octahedral complex. I'm just going to copy this one. So it usually happens in bidentate ligands. So I'm going to rub off all the previous ligands. So remember mirrored versions. Now, the reason you have non-superimposable mirrored versions is that when you have no plane of symmetry, like your hands don't have a plane of symmetry. So which is why the mirrored versions, they look different. Like if you have a plane of symmetry or a line of symmetry, then the mirrored version would not look different. Like for example, our entire, like the human body has a line of symmetry or a plane of symmetry. So the mirrored version, if you look at yourself in the mirror, that looks exactly like you because there's no difference between your right side and the left side. But your hands, they don't have a line of symmetry. I say anyway, so chirality, the concept of chirality it's also over here. Now over here you need bidentate ligands, and we did two of them. So for example, there is NH2 with lone pairs, ethyl diamine. So there's a CH2, and let's say there's another CH2, and they are bonded to each other. Okay, they're natively bonded to our central metal cation, which is copper 2 plus. And here's another bidentate ligand on this side, left side. Okay, so there's another NH2 with its lone pairs. There's another NH2. And you've got CH2 and CH2, right? And we've got another bidentate ligand. It could be any bidentate, as long as there are three bidentate ligands. So you've got another CH2, CH2, and again, the drawing is important. Now, this molecule over here, it doesn't have a plane of symmetry. And if I draw a mirrored version of this, okay, so I'm going to try and draw the. इसको पता नहीं क्यों हुआ. So let's see if I can mirror this. So flip, yeah. So I've mirrored this, right? So the mirrored version is going to be. Yeah, I have to actually draw this again. Just one second. Okay, let me just quickly draw the entire thing, the mirrored version. Okay, you'll be asked to draw this. Okay, so you should know how to mirror molecules. So the molecule on the left, the complex ion on the left, it doesn't have a plane of symmetry. So if you have this CH, this bidentate ligand on this side over here, it's going to be on the left side. So you're going to have NH2, and there's going to be an NH2, and there's going to be CH2 and CH2 over here, and that's your lone pairs, datively bonding. Uh, this bidentate ligand would be on the right side over here. So you're going to have NH2. There's going to be NH2, and they'll be joined together by. And then there is. So you've got all these. So there are two mirrored versions, and they are non-superimposable. That means that no matter how you rotate this, they are not going to look exactly the same. So optical isomers, just like your left hand, right hand, if you have a octahedral complex and there are three bidentate ligands attached to it, then it will have no line of symmetry. The mirrored version would be completely different. TK, it's going to be a completely different complex. So this is my mirrored version. Is this clear?
Yes, sir.
TK, that's it. You'll be asked to draw this. Sometimes you'll have the same thing, but they'll not give you three bidentate ligands. They'll give you two. And this has also appeared sometimes. So sometimes what will happen is you can also have this optical isomerism with just two bidentate ligands. On the third side, you can have a monodentate ligand like Cl minus one. So even then, and let's draw the mirrored version. The mirrored version would be that on this side, you're going to have Cl lines. Okay. So even then, they're going to be mirrored versions. Okay. So there are two scenarios. One is all three are bidentate, then you're going to have a mirrored version. or two of them are bidentate and two of the CLs are, or the two on two sides you've got monodentate ligands. So even in that case, it's going to show optical isomerism. Okay, is this clear?
Yes, sir.
और इसको let me just show you. अच्छा, don't try to study complexes anywhere from the internet, okay? Because uh, don't try to study isomerism in complexes from the internet. I mean, it's a very complex topic. All you have to know is the what I've taught you over here. Okay, that's. I think this one is a better looking image. Just a second. If for some reason. You get that kind of. So that kind of is a simpler version. A lot of times for bidentate ligands, they might just tell you to draw this. Instead of drawing the whole molecule, they might just show you this. So that's two mirrored versions. So next thing, okay, so we're done with complexes. Okay, that's about it. Remember, you'll just be asked very, very simple things about it. You'll be asked to draw this. The drawing is very important. The next thing is we're going to discuss now is why are transition metals colored? Okay, now the theoretical part. So why are transition metals colored? And what's the answer to that? Now that's kind of it's a pretty long explanation. Normally it's a 4 mark question, but you have to study a lot of things before that. The first thing is transition metals have incomplete d subshells. I mean, their stable ions, they contain incomplete d subshells. Now that's got something to do with colors. The d subshells are like really important. So first thing, we need to study the d subshells. So the D subshells and their drawing is also important. So the D subshell looks like this. That a typical D subshell, it's got four lobes. It's like a p orbital. It's like two p orbitals combined together. So so I guess this is so this is our typical D subshell. It's got four lobes. Okay, so I'm just going to copy this. Okay, again this one. Just like you know how to draw your p orbitals, s orbitals, you need to know how to draw your D subshells as well. So the first thing is there are five different types of D subshells, D orbitals. Uh, you've got DXY. So when you talk about the D subshell, it's जैसा P होता है, it's got PX, PY, PZ. The D subshell has five orbitals. It's a combination of five orbitals. It's DXY, DXZ, DYZ, DX square dash Y square, and DZ square. So in total, it's going to have how many electrons? In total, it can have a maximum of कितने electrons होते हैं? That's 10, right? Is that clear? ठीक है, is this clear?
Yes.
F- so maximum it can have 10 electrons. Now, the first one, ठीक है, remember the drawing is important. You'll be asked to draw this. The first one is, it's called the DXY orbital. Now, all of them, they're kind of exactly the same. This fifth one is slightly different, but the other four are exactly the same. The shape is exactly the same. It's only the orientation that's different. So the dxy orbital, it lies in the xy plane. So, and it lies exactly between the x and y axis. So that's your dxy. So you have the x and y axis. The electron density would be maximum between the x and y axis. Then you have the dxc. The dxc orbital, the electron density would lie between the x and z axis. So that's your dxz. So for the z-axis is over here, the x-axis is over here. So the electron density would be between the x and z-axis. Then you have the dyz. So that lies between the y and z. So the shape is exactly the same. The orientation is different. The electron density is now between the y and the z-axis. Okay, so it's in the yz plane. Is that clear?
Yes, sir.
So up here you've got the dx squared dash minus y squared, right? The electron density lies on the x and y axis. And then finally, you have the dg square where the electron density lies, the maximum electron density lies on the z-axis, like a p orbital, but with an electron density. It's like an s and a p kind of merged together. Like there's a donut-shaped area in the middle, and then there's electron density above and below that. But it's on the z-axis. Now, what this is the combined d subshell. This is your entire d subshell. Like you put all of them together, you get this thing. Okay, so that's the whole spherical region where the electrons could be found. So the electron could be between the x and y axis. It could be between the z and which one is this? This is xz. It could be between the x and z axis. The electron could be between the y and z axis. The electron could be on the x and y axis, or the electron could be buzzing in the z axis, right? So if you have two electrons in each one of them, so that means all the spaces around the nucleus are going to be occupied. So it's going to look something like this. Is this clear?
Yes, sir.
Okay, so
Yes.
that's the image of all the 10 electrons, all of them put together, right? None of these regions are overlapping. They're all separate, right? Between the axis, between this axis, between these axes, on the z-axis. That was the only space left. So the last two electrons would occupy the z-axis, right? So that's your d subshell. And you have a maximum of 10 electrons. Now, the thing with the d subshell is that if you look at it carefully, that three of the orbitals, the electron density lies between the axes. Okay, the firstly, the electron densities lie between the axes. While the last two, the electron density lies exactly on the axis. Okay, so remember this is going to be important. So remember dxy, dxc, and dyz, and the other two. So these ones, the maximum electron charge density is between the axes. Whether it's the xy axis or the xz axis or the yz axis. And these two over here, the electron density maximum is on the axis. Is that clear? Is this part clear?
Yes, sir.
So now, so what does that have to do with colors? So what happens is that when a complex ion gets formed, so for example, I've got copper 2 plus. So what is copper 2 plus? It's argon, like all the orbitals over there, and then there is it used to be 3d10 and 4s1, but the 4s electrons are going to go and the 3d would be gone as well. One electron from the 3d would be gone. That's copper 2 plus. So So let's see what happens when copper forms a complex, like any of these complexes over here. Let me draw a simple complex. Let's pick this one. So Okay, let's pick the first one, the first complex that we drew. So that was with water, right? This one. Okay, that was blue. It was a blue colored solution. Yeah, this one. So now what's important is that in an octahedral complex, all the ligands that are approaching the copper 2 plus or getting attracted to the copper 2 plus, they're all coming on the axis, right? For example, this is my x-axis, that's my y-axis, and this over here is my z-axis. So in an octahedral complex, remember we are very specific at the moment, it's an octahedral complex. So all my ligands are approaching on the axis. Now remember the copper 2 plus. What is the outermost subshell of copper 2 plus? That's a 3d9, right? So that means that's a d orbital, right? So in the d subshell, there are orbitals that are between the axes, right? And there are there are electrons that are on the axis, 9 electrons, right? And there are some electrons which lie. So there are some electrons which are going to be lying. Let me change. Which would be lying on the axis, right? Okay, so let's say the green orbitals, right? So this is kind of what the D subshell looked like. There was electron density between the axes, and there was electron density that was on the axis, right? Okay, is this thing clear?
Yes, sir.
Yes, sir.
Okay. So remember, copper ion has an outermost D subshell with 9 electrons. It's slightly incomplete. It's one short of an electron of a complete shell. And all the water molecules are getting attracted to this copper 2 plus. So what do you think what happens? Is it going to be which of the d orbitals would it be harder to keep electrons in? Remember, the d orbital has two types. The d subshell has two types of orbitals: the pink ones, which are between the axes, and the green ones, which are on the axis. Would the green ones face more repulsion compared to the pink ones, or the pink ones? Which of these two orbitals of the d will face more repulsion?
The green ones?
The green ones, right? Because they're right in the way. The water molecules are getting attracted and they're coming on the axis, right? So the green ones are going to face more repulsion. The pink ones are like in the middle, so they don't face a lot of repulsion. Is that part clear for everyone? You clear?
Yes, sir.
So here is
Yes,
this
sir.
clear, Minahil?
Yes,
So
sir.
so what you're going to say is that since the ligands approach on the axis, and this is only for an octahedral complex. So since the ligands are attacking the copper ion on the axis, so the d orbitals which lie on the axis, they face more repulsion. So it's the green ones that are shown in the image. So what happens is that your D subshell, which were previously having exactly the same energy level, they're no longer going to have exactly the same energy level. Okay, they're not going to be exactly the same because the ones that are on the axis, the ones that are on the axis, it's going to become a lot harder for you to keep electrons on the axis. and it would be a lot easier to keep the electrons in the middle of the axis. So the d subshells, where all of the orbitals had exactly the same energy level, they're no longer going to have exactly the same energy level. Much easier to keep electrons in the pink ones, a lot more difficult to keep electrons in the green ones. So the ones on the axis, dx square minus y square, a lot harder to keep electrons in those because there's more repulsion. The electron has to be more energetic and a lot easier to keep electrons between the axes. So dxy, dxz, and dyz. Okay, so it's a lot easier to keep electrons over there. And that kind of creates an energy gap between the two. Okay, so the electron would prefer the pink areas, the pink orbitals. It will not prefer the green ones. Is that part clear?
Yes, sir.
Yes, sir.
Okay. So if there were no water molecules, then all the orbitals were exactly the same. But now, since in the presence of water molecules, they're not going to be exactly the same. So how many electrons did we have? We had 9 electrons, right? So the electrons would prefer the between the axes, the one which has the lower energy level, right? There's less repulsion over there. They don't prefer the ones on the axis, right? Now, why are they colored? So the reason why they're colored is that electrons in a complex, there is light falling on those electrons, electromagnetic waves of all sorts, whether it's gamma rays or X rays or red light, yellow light, blue light, all these frequencies are coming in. This energy gap, an electron from the from the lower energy d orbitals would absorb a frequency and would jump to a because there's space available at the top. So it will jump to a high energy orbital. But for that, it needs to absorb energy. And to absorb energy, it will absorb a specific frequency, right? So, so the thing is, like if you look at this orbital of all these orbitals over here, the electrons prefer the pink orbitals over here. But if you make them very energetic, they're going to start absorbing photons or frequencies from the visible light, and they'll start jumping and move to a region where they're going to be in a higher energy state because they'll be facing a lot of repulsion. So they're going to jump around between the pink orbitals and the green ones, right? But to go to the green areas, they need to be very, very energetic. Is that clear? So
Yes.
they need energy to go into the green areas. So which is why they're going to absorb frequencies. And the thing is, the reason you see colors is that this energy gap specifically, it exactly matches frequencies that belong to the visible spectrum. Like if you had a slightly bigger energy gap, then you'll be absorbing higher frequencies, which might not be in the visible spectrum. If you had a slightly smaller energy gap, then you might be absorbing frequencies that would be very low, like radio waves. But luckily, this energy gap that gets created, that exactly matches frequencies that belong to the visible spectrum, which is why you see colored compounds because all sorts of frequencies are. I mean, you have all sorts of your entire white light. What does white light have? It has all these. It has violet frequency, indigo, blue, green, yellow, orange, and red. So it's not going to absorb all the frequencies. What it will do is maybe it absorbs just the yellow frequency. So when the light bounces off, there's going to be one frequency missing. So let's assume that the electrons jumping around in the d subshell, they're absorbing the yellow frequency. So what is left then? You got violet, indigo, blue, green. There's no yellow now, so the yellow is gone. So that's gone, and you're left with orange and red, right? Is that clear?
Yes, sir.
So any one
Yes,
of the
sir.
fre so any one of the frequencies would go missing uh, when the electrons jump around in the d subshell. So you always see a complementary color. So if it's absorbing yellow frequency, you're the person who's standing over here. So you won't see yellow. You get the point? You will see all the other colors, but you won't see yellow. Is that clear? Okay,
Yes,
so
sir.
so the person who's standing over here, he's going to see the all the other colors apart from the colors that the transition metal complex and the electrons in the d subshell jumping around are absorbing. So normally what happens is you get a complementary color. So there's a way to figure this out, that you draw a circle, and to figure out the complementary colors, what you can do is so you got violet, indigo, blue, green, और क्या होता है yellow, orange, and let's say red. ठीक है, so I've distributed them. So what normally happens is that if the yellow is gone, what do you see? You see this. You see the opposite side. I mean, if from white light you remove the yellow color, the rest of the colors are going to mix, and this is going to be the average color, something between violet and indigo. Is that clear?
Yes, sir.
Yes.
Okay, so similarly, if red frequency gets absorbed, you see the one that's opposite, something a mixture of green and blue, right? So so you can think of it this way, uh, that you can spread out the frequencies and always a complementary color is seen. If orange is absorbed, you would see the opposite side, which would be something a mixture of indigo and blue. If blue is absorbed, you'll probably see something that's red and orange, right? Something a mixture of red and orange. So so always complementary colors are seen. ठीक है? Is this clear?
Yes, sir.
ठीक है? So remember, the D subshell had exactly the same energy level initially. And when they have exactly the same energy level, there's a term that's used that's known as degenerate orbitals. That means they are exactly the same type, same energy. ठीक है? For example, px, py, pz are degenerate orbitals. They're exactly the same energy. The orientation is the only thing that's different. But when a complex is formed, so I'm just going to repeat everything. When a complex is formed, uh, then they're not exactly all the same. In an octahedral complex, it's a lot harder to keep electrons on the axis compared to between the axes. So, so on the axis, much harder to keep electrons. Electrons have to face a lot of repulsion, which is why they have to be very, very energetic. So they go to a higher energy level. Between the axes, a lot easier to keep electrons, so they don't have to be very energetic. So they have a lower energy level. And the electrons can switch between these orbitals. They can move around, but for that they need to absorb frequencies which belong to the visible spectrum. So it's going to be a 3-4 mark question. They might ask you to draw diagrams, but the answer to this question is, we'll start with like that. The answer to this question is, why are they colored? So it's a 3-mark question, 3 to 4 mark question. And so you're going to write that due to repulsion from lone pairs on ligands, the D subshell splits into two. So remember, the drawing is important. They're going to ask you to draw the D subshells. They're going to ask you to draw the D subshells at the higher energy level. They're going to ask you to draw the D subshell, which is why the whole explanation would be important. Okay, but this is going to be the 3-4 mark question answer. So the d subshell splits into two energy levels. Electrons from lower energy d subshell gain energy and move to high energy d subshell. Look at d orbital, not subshell. Subshell is the whole thing. Electrons from the lower energy d orbitals gain energy and move to higher energy. And the next thing is the energy gap that we are talking about. Delta E matches frequencies that belong to from the visible spectrum. Since E is proportional to, since energy is proportional to frequency. So it exactly matches frequencies from the visible spectrum. Hence, a complementary color is seen. Okay, so that's going to be our 4 mark answer.
सर हायर एनर्जी ऑर्बिटल्स आर जो वो एक्सिस में होंगे.
हाँ, octahedral complex में the one that lie on the axis.
ओके.
ठीक है.
उसमें सिर्फ ऑक्टाहेड्रल के लिए पूछा जाएगा.
Nee, they're going to ask you about tetrahedral as well. So in tetrahedral, the ligands don't approach on the axis. ठीक है. So in tetrahedral, we'll discuss tetrahedral in the next class, ठीक है, in detail.
ओह सर.
But like, is this clear that? But and remember, the answer has to be exactly this. Due to repulsion from lone pairs on ligands, the d subshell splits into two energy levels, and the electron from lower energy d orbitals gain energy and move to higher energy d orbital. Since and the energy gap delta E matches frequencies from the visible spectrum. Since energy is proportional to frequency, and hence you see a complementary color. Okay, so right now we've just done octahedral complex. Okay, and this is probably going to be the last thing. Okay, uske baad I guess this topic would be over. Uh, the drawings are important. They're going to ask you to sketch this. You need to know which ones are going to be higher energy, which ones are going to be low energy. They're going to ask you about what color gets absorbed. So this wheel over here, like if they tell you blue is getting absorbed, you should know that uh you would see something that's orange red, right? You can make sure you know this as well. So चलो ठीक है. Are there any questions on this? Is this clear?
हाँ सर, कैन टेल अगेन इनका एनर्जी कैसे आती है इलेक्ट्रॉन के पास ताकि मूव करें.
नहीं, lights है ना, by absorbing frequencies from.
अच्छा लाइट से. ओके.
ठीक है.
सही.
तो इसीलिए ना वो the person who's standing over here, if there's Vibgyor, if there's white light coming in, Vibgyor is white light, right? So
सही है.
अगर if the electron absorbs yellow, right? So the person who's standing over here is not going to see yellow.
ओके सही. ठीक
ठीक.
है.
चलिए ठीक है. Let's continue tomorrow then. ठीक है.
ओके सर.
Thank you, sir.
Okay, take care. Hafiz.